Hi everyone, welcome to Statistics Late at Night with me again. Uh, as you can see, I'm almost ready for bed, but I wanted to really take this time out of my day to really just try to do my best to give you everything I know about a topic called linear regression, so that hopefully it's easier to understand and easier to stick in your heads for when you need it. So basically, with linear regression, what is happening is we have variables in data. So in this Excel document, I have years in experience and salary. But if we're in the professional world, we might have also material on college degree. And we might also have material on, let's just say, referred to the position. We might also have material on major projects and so forth. That gives us some element of data and relationship with data. And we're looking at this stuff, and in our managerial decision making, we're asking, can we form a relationship? Is there an actual sort of connection or pattern between data that can help us make decisions? If there is, that's great, because we can see what our normal functioning is and actually predict what will happen if we change what will happen. And so often what we'll do is say, maybe as a manager, I'm concerned about, am I giving new hires the right salary based on their years of experience? And so I'm going to take lists of data of all the salaries and years of experiences of my employees, and I'm going to plot them. See, is there a relationship at all between salary and years of experience that I can use so that I can say, if a new hire comes in, I'm going to give them their salary appropriately based on how many years of experience they bring in. And so as a manager, I'm making that decision based on like all the different possible variables. Even, college degree might be involved, referred to the position by another person might be involved in my decision making as an HR sort of manager. But I might just say, I'm only concerned about years of experience and a salary. And I want to know, is there a relationship that I can use to inform my decision making? Or is there not? And so I've drawn what this data might look like, years of experience and salary. And usually this is the first step that any data analytics person would ever do when making a regression. Because what they're asking first and foremost is there enough evidence, even at its very basic level, that I can conclude that maybe this is worth looking into and that there's a relationship that matters to me that I would want to know. And so how you read this chart is what I just graphed is that years of experience is in your IV section of your chart. Salary is in your DV section of the chart, or your Y section. Years of experience is in your X section, or your X axis and Y axis. And how you read this chart is, if there's a relationship, you are predicting a person's salary based on their years of experience. And it really just depends on what you want to predict. You can actually flip these with algebra, but I want to really make that relationship clear with linear regression. One of your variables is going to be a dependent variable. It's going to be dependent on changes on your IV. And one of your variables in linear regression is going to be your independent variable. It's going to change, and as a result of these changes, it's going to affect your overall salary. Now here's the thing. Here's what linear regression really says. It says take data And I want to know, is there a relationship? Can I actually draw a line through this that roughly resembles all the data points really well? Like the line I just drew right now. If I can, then it means that I have a linear relationship. And a linear relationship might best be represented by something that looks like this. All the data points are sort of closer together so that you can actually draw a line, because it sort of, the data sort of personifies a line. If you had something like this would be like an exponential relationship, because the data is personifying exponential growth. Or you can have a parabolic relationship or other relationships. This is what linear relationship is concerned about. Does the data cluster around the line? Is there a little variation around the line, so much so that we can assume that maybe we can predict one from the other by using a line equation? And I'm emphasizing line because that's really what matters here. And in my first graph, there's really no relationship among these. If I just drew a line like that, you could say maybe, but there's enough dispersion around there that when you look at it, you're like, it doesn't really seem significant. And so how you would mark no relationship is it's a linear horizontal line like that. Remember, in geometry, this line, the slope on it, is represented by rise over run. There is no rise. There's only run. So you're getting a slope of 0 of your m. So how you represent no relationship is that there is actually no difference in dv when you change iv. If you grow x, and you grow x, and you grow x, and you're changing x with a linear line, if I go over here, and I go over here, and I'm changing x each time, y is not changing. And so there's no relationship at all in a linear line like that, in a horizontal line. And again, go back to geometry. It is a slope of 0. There's no relationship. And it makes sense. This data is really dispersed so that you can assume that you can't really judge if there's a relationship or not. When you're looking at it, it's just a cloud. It doesn't have a connection point to what you might consider a relationship or something. But let's take a look at what you might do if there is a relationship and how you might know that based on the data you've been given. And how, if you're a manager and you're looking at data from, your reports, or from you gather from your systems or something like that, and you really want to know, is there a connection between variable 1 and variable 2? How might you find that? So I'm going to delete these parts. I'm going to start right here. If I was concerned I had years of experience in salary as part of a larger data set, and I wanted to know if they're connected. The very first thing as a data analyst that I would do is I would highlight both, and I would actually draw scatter plots. So highlight both like this, and I would go to Insert, and I would go to Scatter, which is this one, Insert Scatter. And I would click the dots. What Excel automatically assumes when you do this is that your column A, your first column, this is going to be your IV on the bottom here. And your column B, your second column, is going to be your DV. Now this looks like a line, right? I mean, it just looks like the line. Now I can sort of support that by, if I click on the chart and I go to chart design and I go to add chart element and I go to legend. Sorry, I go to trend line. I can click linear. And look, it graphs a nice little line that sort of maps these data points around it very easily. And so now, as a data analyst, I've created a scatter plot based on two variables that I think are related in some way that I might want to use in the future for what I do. And now I know I can. I know this is a linear relationship and that linear regression might be a particularly valuable data analysis that I can apply to this data to really use it to help me predict what I should be paying people based on their years of experience in my company. So let's run that regression now so we can see how to do it. I'm going to delete. So that was a relationship, first of all. That was, when we did that scatter plot, we found that there was actually a relationship between the IV and the DV. They were all sort of clustered around the line. That's what our data looked like when there actually was a linear relationship. But remember, our data when there was no relationship at all between two variables looked like a giant cloud. And we represented that no relationship with zero slope. And so your slope, your M, tells you what strength or magnitude in a way your relationship is. The more your slope is greater than 0, the more you have evidence for that there's actually a relationship there. And this is a key point because what linear regression, when we run it, is going to test, and let me get my pen back, is a null hypothesis that your M or slope is equal to 0. There is no relationship at all. And the alternative hypothesis that your slope is not 0. That there is a relationship, that you have a slope significantly different than 0, indicating that there's actually a connection between your two variables and that they're holding on to each other or influencing each other in some way. And that's critical to really understanding what the numbers are, because this is the test that the multiple and linear regressions run. Is there a relationship or is there not between your variables? And that's the test that is tested. So let's keep going, shall we? Because we should get into this, the actual numbers. So I'm going to erase everything. And I'm just going to leave those dots to save time. So to run the regression, what we do, so I got to click out of everything first. We go to data. To run this regression, we go to data analysis. We click it. Then my computer's thinking. And what we want to do is we want to go to scroll down and go to regression. Click OK. Our Y, just like I described at the very beginning of today, the Y is your DV. It is the thing you want to predict based on the relationship you think exists. So in this case, I want to be able to predict what salary should I give people based on the years of experience they come into my company. Input X range is the IV. It's what you want on the X-axis. It's your years of experience. And I just highlighted that just to show you again. I click on this up arrow and I highlight years of experience. I've highlighted the labels, so I want to click that. It's always good to click the confidence level, although it's not a requirement. This also allows you to define what confidence level you're really looking for. And then I always like to put a regression and all my data in new sheets just to make it clean. And then you can click some of these residuals. I don't necessarily feel like you need it, but it's additional information in your regression if you want it. Now click OK. And we got this, our output. Now, what's really important to understand is exactly what information are we given here. Because that's going to define really how successful you are in really understanding what regression is. Because back in the day, like in the ancient times, when they just used a calculator where you punch the buttons in, all this math had to be done by hand. But nowadays, because our data sets are that much bigger, because we have that much more data we're applying, you really, in regression, can't use a regular calculator to solve this anymore. There is a way to do it by pure math, but there's just so many data points that 9 times out of 10 in most workplaces, you're solving this by an Excel or by a program like Gretel or by a program like R or Python that can really do this massive amount of statistics all at once very quickly for you. It's the magic of computers, right? And so you got to understand what this computer is spitting out when you pull this off. So let's do it. So I'm going to highlight a couple things here once I get my drawing back. So this intercept right here, this intercept, that stands for your y-intercept. Remember, we're dealing with lines. It's a linear regression for a reason. So y-intercept. This coefficient right here is your y-intercept. If you were to write this equation of the line that's trying to predict your dv from your iv, then you're right, y is equal to mx plus your y-intercept, which is 25792.2. This, years of your experience, is your slope. This is your m. So it's y is equal to 9449.96x plus this 25792.2. And just to give you a hint of why that's that, if you go back to your data, notice that your salary goes from 30K to 122K approximately. So you need, if you're going from 1 to 10 in years of experience, that slope is going to change. Each time you add another years of experience, that slope has to change somewhat significantly. And that's why you have a significant slope. There's 9,000 in your coefficient, approximately. Now here's the key. You have an equation now. Y is equal to 9449.96x plus 25792.2. This x is your years of experience. And this y is your salary. This equation we just made using these two coefficients, it's what's called your linear regression equation. And it allows you to predict. So if I had someone that came in with 4 years of experience, I could now solve this for what salary I should be giving them. And so, for example, let's do this in Excel. 4 years of experience. and I go, the equation on my line is this number, the 9, 4. Let's make sure I'm highlighting it. I'm just going to write it in. It doesn't seem to want to highlight for me. So it's equal to 94.96 times my years of experience, which is 4. And then all that plus my B, which is my intercept, which is 25792.2. Enter. And what we just found was that our historical data that we have taken on our past years of experience and salary is indicating that if we wanted to continue paying people in the same respect and in the same pattern, someone with 4 years of experience, we would pay them that much. And you can go back and forth with this linear equation. If you want to try to predict years of experience from the salary that a person has, you can do that. But you can see how this is useful. I mean, it allows you to really take stock as to what you've done and allows you to say, do I want to do the same thing again? Couple more small points and then we're done with really the basics of what we just did. So the second thing I want to draw your attention to is this p-value for years of experience. Remember, this is a slope, this is the p-value. And remember, our basic test is our null is that there is no relationship. And I'm going to try to express that a little better. That there's no R or slope or slope is equal to 0. There is no relationship between years of experience and salary. Now, H alternative is that there is a relationship, that slope is actually significant. Slope is not equal to 0. So what this p-value is testing is it's saying, okay, this p-value is for our slope. This is our test. This p-value is definitely p is less than A, or p is less than alpha for our slope, so that our slope has significant enough evidence that it lies in the rejection area. And what that means then is that we have a slope that's significantly different from 0. We must have a relationship then between years of experience and salary, something significant that we should actually be paying attention to. The final part I really want to talk about is this R squared and this adjusted R squared. A couple points to this. I'll talk about adjusted R squared in another video, but this is really having to do with multiple regression. And so if you're just performing regression amongst 2 variables, you never have to worry about it. It's really only for multiple regression. This R squared, this regular R squared, is expressed by the following formula, which is 1 minus the sum of squares of your residual over your sum of squares total. is equal to r squared. What that is a measurement of how well your data clusters around this linear line that you have created. And so let me sort of diagram this out a little bit. If you have a set of data points, let's just say 4 data points, and you would try to fit a line to it, it might look like that. Our sum of squares residual is merely this distance to that regression line that you calculated. And in fact, it's represented by that. So it's represented by I think it's P or X, I can't remember which. Pi, representing your data, minus P hat or P caret, whatever it is, I don't remember, but it's represented by this value minus whatever this value is to get that distance. Then the next part is sum of squares total, which is right down there. That's saying if you have these numbers, how much different is that if you had no relationship? We're assuming a relationship. So we've tried, when we calculated the sum of squares residual, we've tried to map the perfect linear line in our data so that there's not much difference between our data and our line, as much as we can minimize that as possible. So this is always going to be a fairly low number compared to the total. And as you can see with our data set, it is a fairly low number compared to the total. The total is, let's see, it is 21 billion. And the sum of squares residual is 938 million. Sum of squares total is going to be your maximum amount of dispersion. Because you're assuming no relationship, you're no longer trying to do anything possible to try to minimize the distance between your data to your line. And so what's really happening when we do R squared, and what's really happening when we are doing this, is we're saying, and I'm going to start a new worksheet to describe it. We're saying r squared is equal to 1 minus the sum of squares residual over the sum of squares total. Then let's just make sure I did this equation right. And so I want to take what is the minimum amount of deviation from our line that we've created over the total possible deviation from our line that's physically actually possible with our data. And I'm going to get a percentage. And that percentage is going to represent the percentage of deviation taken up that's still left over. It's going to represent, the best way to put it is it's going to represent, this is sort of how imperfect our line is. And then 1 minus that is going to represent how closely fit our line is. Because it's the exact opposite, it's its complement. So if sum of squares residual is how far away our data is from our line, is from our line, that we're trying to fit to it, sum of squares total is the total amount of deviation then this comes out to a percentage that's this, how imperfect our line is. The exact complement of that is how closely fit our line is, how good of a fit that we have with our IV and with our DV. Or in other words, your R squared is how close of a relationship these guys have. If you were to take all your data from your years of experience and salary, do they closely predict each other? If you put 1 year of experience, is it going to be exactly the salary of all your people with 1 year of experience? Or is there some subtle difference? And that's sort of what R squared is. And then taking it further, what you'll find is that this adjusted R squared, and I'll try to highlight it for you. That adjusted R squared stands for how closely is that fit when you add more variables to this model. And then, right now we've sort of talked about the main features of this. There's not much more we can talk about. I will get into some of this other stuff in another video. I do want to emphasize a little bit that this lower and upper 95%, we clicked 95% first when we did this. So if you remember, go back to the data analysis where we actually started to run this data. And we clicked specifically 95%, but we are given two 95% by doing so. I'm going to highlight that part. But what we do is, if we want a 99% for say, it's going to automatically give us 95. We can just type 99 in the box and get something different on the other half. Notice how these are the exact same numbers because we kept it at 95 in that box. Finally, understand a little bit about what these numbers mean. When I look at these bottom two, these two, what they're really saying is that we are 95% sure, and these are slope values, so slope values in our interval, we are 95% sure that the true slope of the relationship between salary and years of experience lies between those two numbers that are right here. And again, this is basic regression 101. I really sort of tried to lay it out for you in every single step of the way, what's really going on. In the end, we're looking at relationships. Do we have a relationship? How close is that relationship? And can we use that relationship to predict the IV and the DV? I hope this was helpful, and y'all have a great night, all right? Bye.